Okay, we can start. This is a summary of my previous lectures. The first important thing is that I declared that there would be no references, not because they shouldn't be there, but in order to help the flow. This is based on work that was done by thousands of people over a long period of time. There's an almost complete list of references here. That's all I say about that. Then, in the first lecture, we discussed global symmetries, and we limited ourselves to the simplest case, known as zero-form global symmetry. These are the simplest ones. There are various generalizations, which we can discuss, but let's first get this one straight, because it turns out to be more subtle than people usually think. And we talked about internal symmetries. These are symmetries that do not act on the coordinates. But we also introduced a very surprising notion of eminent symmetry, symmetry that does not exist microscopically, but it appears macroscopically not as an emergent accidental symmetry, but as a symmetry that is not even violated by, it can be violated by relevant operators. Sorry, there are relevant operators that could have violated it. There are also irrelevant operators that could have violated it, but none of them are present. So that's a very surprising notion that goes against the standard picture, and I presented it from a number of different views, and today I will present another view of the same thing, connecting it to other phenomena that are well understood. Then we discussed anomalies, and the modern view of anomalies that we couple the system to background gauge field, and the partition function is not gauge invariant. There are various ways of characterizing it. We limited ourselves to flat gauge fields. Space was a circle, Euclidean time was a circle, and that's all we did. And the key equation that we had is if we twist a space by a group element G of the internal symmetry, G, then performing complete rotation of space is the same as the group element. This is basically the statement that we have twisted boundary conditions. But as we saw, this equation has very profound consequences, which are usually not being taken completely into account. Then we studied the Hilbert space of the twisted theory. Yeah. There could be more things. There could be. So, for example, if space-time is a sphere, then there are more options. I'm not making any claim that this is the most general thing we should study. I'm only saying that this is a thing that we can study. And as you saw and as you will see, we can get enormous amount of mileage just out of that. Of course, we should generalize it in all possible directions. So this equation will play a crucial role, especially today. And then we demonstrated all that in the C=1 compact boson, both in the continuum and on the lattice. We presented a particular lattice model that has both the momentum and the winding symmetries. It has anomalies. And this equation played a crucial role, and I will review it later today, where we twist both by momentum and by winding. And then this equation could not be satisfied on the nose. So on one hand, this is a trivial equation. If we twist by a global symmetry, it's clear that if we do a complete rotation of space, the operator that performs it should be equal to the group element of the twist. And on the other hand, we saw that this was not possible in the twisted boson, in the compact boson when we have twisted boundary conditions, and that was a signal of the anomalies. And I will present that soon. And that's kind of a summary of what we did. Are there any questions on that? None. So what I will do today is try and take all these ingredients and apply them to in another context, which is a context of almost a century, which is almost a century old. This is a system known as the Heisenberg spin chain. It was introduced by, I'm not giving you the answer, you can figure it out. And it was first solved analytically by Bethe, also a long time ago. There's an exact solution based on Bethe ansatz. And you could ask, okay, if it's exactly solvable, why do we care? We care because we can start deforming it in all sorts of ways so that it's not integrable. And then we would like to see what we can say about this system. This system is important in condensed matter physics as a toy model for, or as a description of various phenomena. And it's also a good model for quantum field theory. So that we'll do today. And we will study the global symmetries. We'll follow the same recipe, the global symmetry and the anomalies. And we'll see that on the lattice we have a lot of anomalies. And these anomalies on the lattice have consequences for the long distance behavior. And they are known as the Lipschutz-Matisse theorem. So this is again something which is more than half a century old. Over the years there have been many proofs of the Lipschutz-Matisse theorem. So it's often abbreviated as LSM. Then Oshikawa did some work. So some people added O, and some people in Hastings generalized it. So some people add the H. There's huge literature on that, which I'm not going to refer to, nor am I going to use. I'll present another version of the story, which is built on elements by these authors, but will follow the line of reasoning that I presented here. And then we'll take the continuum limit, and we'll see how various subtleties in the lattice model are mapped to things we know in the continuum theory. And if we have enough time, we will see that even though the lattice model is quite complicated, we can still write exact formulas for some of the lattice observables. And these exact formulas for the lattice observables will lead to new insights on, into how these symmetries arise. Okay, this was a long introduction. So now I'm going to start writing formulas. So what's the model? We have a one-dimensional spin chain with periodic boundary conditions and L sites. Point number one, which I think I already said before. I'm not going to take, step one, I'm not going to take L to infinity. L is finite. We have a finite dimensional problem, finite dimensional Hilbert space, unlike the examples of last week. Here we have a qubit at every site, or a two-level system at every site. So the Hilbert space is finite dimensional per site. And we are going to study this system as is. We would like to see a global symmetry and anomalies, what the precise global symmetry is, and so forth in this symmetry, in this problem, no limit. And the literature is a bit confusing because people go back and forth between the lattice and the continuum. And it's true that there is a map between them, which is essentially a 't Hooft anomaly matching, as we will see. But it's absolutely crucial to keep two distinct stories. Story number one, on the lattice, finite L, and we'll study that in a lot of detail. Story number two, the continuum theory and its properties. And story number three, there's a map between them. And we should not mix these distinct stories. It looks complete, when I say that, it looks completely obvious, but if you go through the literature, it's important to keep these stories separate. So the Hamiltonian, I put a 2 for no good reason. There's a sum over J from 1 to L. It labels the sites. We have periodic boundary conditions. S at the point J, S at the point J plus 1. Okay, this thing as it stands is the Heisenberg model. And we can change it in several different ways. Number one, we can add here, which I'm doing in another color, alpha S, Sx, J, Sx, J plus 1, and we can put alpha Y, Sy, J, Sy, J plus 1. This addition breaks the global symmetry, and there's a name for that. We have just the black one. It's called the Heisenberg chain, SO3 chain, or XXX chain. If we deform only one of them, so we add only that, so people call it the XXZ chain. If we have all of them, people refer to it as the XYZ chain. So there's a two-parameter family of Hamiltonians. What I'm going to say works for any generic value of these alphas, but for simplicity, we'll set these alphas to 0. Yeah. Excellent question. This is an antiferromagnet, not a ferromagnet. The behavior is different if we have a minus. And for the next half an hour or so, it will make no difference. For the next half an hour or so, what I'll be using is only that we have an SO3 symmetry. In fact, it's enough to have Z2 times Z2. If we add all these different couplings, we have just Z2 times Z2 with any coefficient in finite L. And for at least the next half an hour, it will make 0 difference.
Yeah, but then you don't really have the extension.
Yeah, I have translation symmetry.
Because you want to have this.
Are you talking about the solution? There is a translation. I'll discuss translation symmetry more than you wanted to hear. You will regret asking this question. The main tool I'll be using here is translation symmetry. And you will see that translation symmetry acts in an interesting way. And what you just said has enormous consequences. But for the moment, I don't know, I didn't analyze the Hamiltonian. You put some more detailed knowledge, you know, it goes up and down. I just wrote something that is SO3 invariant. Okay, and since you asked, so what is the symmetry? First of all, there's an SO3 symmetry generated by S, no index, S sum over J, S vector J. That's an SO3 symmetry.
Another parameter, the coefficient of the SS?
That doesn't matter because I can absorb it in the temperature. Because I write e to the minus beta h, so if there is a beta, I can absorb it in that. So let's set it to 1.
Or in the H.
Sorry?
Or in H.
Or in h, and then you can say that beta is always sigma. I'd like to dial beta because that would compare large beta, where I see the full Hilbert space, and small beta. Large beta, where I focus on the low energy state, and small beta, where I see the whole thing. But for the moment, I don't want to take any limit. L is finite. In fact, I will analyze this system for L equals 2 and 3 and 4 later in the talk, and you will see that all the things I'm doing can be seen in this elementary step. And since you asked about translation, there is a translation symmetry. I'm picking the basics of the Hilbert space, M1, M2. I'm diagonalizing SZ every side up to ML. And these M's are plus or minus a half. And that maps it to ML, M1, ML minus 1. So that's a well-defined operator. I told you exactly what it does on every basis element. And you can check that it commutes with the Hamiltonian.
Just the black one, right?
No, even with this kind. It commutes with the, this operator commutes with the Hamiltonian even when the alphas are non-zero.
Yeah, but so my question was if we're now thinking only about the black Hamiltonian without the blue addition? Yeah.
It's still true. This symmetry is a true symmetry of this system with or without the blue terms. Sorry? It's ZL. The group is ZL. The group is ZL. And this ZL is true whether I put a plus here or a minus here and whatever. I can also modify the system by adding couplings between more sites.
ZL plus 1 is Z1.
SL plus 1.
SL plus 1. The circle.
Yeah. Okay, so when I wrote this thing here, when I had here L plus 1, it's the same as 1, this will be crucial. So this is the system.
Sorry, in your notation, does the first black term include the Z term and also not X and Y?
Sorry?
Does the black term...
The black term includes all of them. It's a sum over all of them.
Yeah.
Preserves SO3. I made a mistake. Ignore this thing. It doesn't exist. I just wanted to tell you that what I'm going to say is much more general. So I wrote some terms that are very popular. In fact, it's really worth understanding what is not true when we add them. But for the beginning, we can study any of them. And we can also introduce next to nearest neighbor interaction. All I impose is SO3 and this ZL. And if you wish, there's also parity. So the symmetry is DL and not ZL. Subtlety number 1, that I'm very glad that nobody asked about it. You could ask, why did I write SO3 here? Because e to the 2 pi I Sx, S is the sum of all of them, is minus 1 to the n. It's also the same for e to the 2 pi I Sy and e to the 2 pi I Sz. Therefore, this Hilbert space, when L is even, is in an SO3 representation. When L is odd, the Hilbert space is in a projective representation of SO3, but the correct symmetry group of the system is SO3, not SU2. In fact, we worked that out for L equals 1 in the first lecture. We had just one qubit. So the global symmetry is SO3, and it's realized projectively when L is odd. So what do? We presented a recipe. We should subject the system to background gauge field. Sorry. So what's a background gauge field? As we move around space, we perform a transformation by SO3. So we would like, so as we move around, there would be G, which would be an element of SO3. And without loss of generality, I can let G be e to the I sigma SZ. Everything else is conjugate to that. And I would like to have a defect for that thing. So we discussed that in the first lecture, that we have these different ways of presenting things. There's a defect, like connection. We can spread it around. We can spread the connection around. We can put it in the transition function and so forth. So I'm going to write the Hamiltonian, which depends on sigma. And I'm going to write it as 2 sum over j from 1 to L minus 1 Sj vector dot Sj plus 1. So I single out the link between L and 1. And then I'm writing e to the minus I sigma S plus L S minus 1 transformation conjugate plus twice Sz L Sz 1. So I took one link, this one, and I conjugated here by this group element. In terms of lattice gauge theory, I turn on a background gauge field here. Notice, among other things, that even though, so the symmetry is SO3, so indeed sigma is the same as sigma plus 2 pi, so the Hamiltonian is the same at sigma and at sigma plus 2 pi, even though the Hilbert space, the local Hilbert space, transformed projectively under that transformation. If you wish, there are two minus signs from the two sides and everything is okay. So we're going to study it, or if you really want school, S plus minus, in my convention, is Sx plus or minus I Sy. I don't think a 2 or 1 here. So the first thing we see is that h of sigma plus 2 pi, so it's the same set of exercise that we did last week. We check, is it a good thing if I change sigma plus 2 pi? That's manifestly true, the same outcome. What about the fact that the defect should be topological? It should be such, as we discussed last time, that if I put the defect on one link, on another link, I should get the same system. I shouldn't get the same Hamiltonian on the nose, but they should be conjugate to each other. So that can be seen by conjugating by e to the I minus I sigma Sz at site number 1. So if I conjugate by that, this is L, and this is 1. If I conjugate by that, it sets this to 1. So sigma here and 0 here and 0 here is mapped by this conjugation, is mapped to 0, 0, and then sigma here. So the defect is topological. And now we can ask, okay, before we discuss other things, I want to say a few more things about the symmetries. What are the distinct values of sigma? So first, by performing an SO3 rotation, I can put everything in the z direction. But there's another transformation I can perform. It's a Z2 transformation generated by R for reflection e to the I pi Sx. This is pi rotation around an orthogonal axis. It does not commute with the Hamiltonian, but it maps sigma to minus sigma. More mathematically, the conjugacy class in SO3 is labeled not by sigma between 0 and 2 pi, or with 2 pi periodicity, but sigma should be identified with minus sigma, because I can do a 2 pi rotation in an orthogonal direction and bring it back. And one way of saying it is that h minus sigma is this transformation R, h of sigma, R inverse, and you can check it for yourself. So when it acts on all the sites except those near the defect, trivially commutes, and around the defect it flips the sign as it should, and it flips the sign of sigma. So they're conjugate to each other. And what's the internal symmetry? The internal symmetry group is the subgroup of the original SO3. So originally we had SO3, but now it becomes a subgroup, which is the centralizer of the group element. These are the set of transformations that commute with the Hamiltonian. So for generic sigma, so this G of sigma is for sigma equals 0, there is no defect. So we have the full SO3. For generic sigma, we have O2, and for sigma equals pi, we have, sigma equals pi. Sigma equals pi, we have O2, and for sigma not equal to 0 pi, we have U1.
Not equal. Not equal. No.
Not equal, yeah, not equal. Yeah, thank you. Thank you. So that's the group element. And what else do we have as a symmetry group? First, this is the internal symmetry. That's completely easy. We also have translation. What happens to this ZL? So I'm basically doing what we did last time. ZL, this symmetry is not a symmetry. It does not commute with the Hamiltonian because the defect is in one place. But I also said that the defect is topological, so we can conjugate and move the defect back. Therefore, I define T of sigma to be e to the I sigma SZ at the point 1 times T. So I first shift by the operation of T, and then I move the defect back. This T of sigma commutes with the Hamiltonian, with this Hamiltonian. And therefore, the defect is topological. Otherwise, we have nothing to talk about. Okay, so this is our goal. Study the Hilbert space with this Hamiltonian. This is the Hamiltonian we study now. We know its symmetries. We discussed its symmetries. And let's check how the symmetries are realized. So these operators satisfy some relations. The relations in G sub sigma are, we'll soon discuss them. What do I need? I need almost everything. Okay. Number 1, T of sigma raised to the nth power. For sigma equals 0, it was 1. And now what we have is e to the I sigma SZ. Because if you take this thing, where did I write it? Here. If you take this thing and you write it L times, you can slide these T's around. When you bring all of them to the end, you get 1. But then you have in the exponent the sum of the SZs, and the sum of the SZs gives the symmetry transformation. Well, earlier in the talk, I mentioned this is a general result. Complete translation around space is the twist rotation, is the group element. This is the statement of twisted boundary conditions. So we see that here, the way it acts on the Hilbert space. Now, we could have redefined T redefined T of sigma by bringing the nth power, 1 over nth power of that to redefine T by that. But then, away from the defect, this T will not act as in the untwisted theory. So this gives us a preferred normalization. To point you to something we'll have later, we'll later discuss anomalies in all these symmetries. We'll check what is realized projectively. And we'll have to choose some phases. There will be some freedom in where we put the phases. And there is some freedom here, but there is a natural choice. And the natural choice is that the defect is localized, and we want the operators away from the defect to act as if there is no defect at all. So that defines the phase. Now comes another equation. The Hamiltonian at sigma, and sigma plus 2 pi is the same. But T of sigma plus 2 pi equals minus T of sigma. What did happen here? I said that the Hilbert space, if L is even, the Hilbert space is periodic in sigma plus 2, is in a representation of SO3. the fact that one site is in a projective representation doesn't matter when L is even. When L is odd, it does matter. We said that. But now I say that even if L is even, there is this operator, the translation operator, that knows that one site is in a projective representation. So I could have done it by just acting with e to the I alpha times sz at one point. Then I would detect the minus sign. But that's not a symmetry operator. The point is that this guy is a symmetry operator. It commutes with the Hamiltonian. This is the symmetry of the system. And something in the symmetry is interesting. The symmetry operators mix. We have a relation like this. The ZL and the SO3 mix through this equation. And one of the generators is not periodic as we shift sigma by 2 pi. Again, we could have redefined T sigma goes to T sigma e to the I sigma over 2. Then I will not have a minus sign here, but I will get some funny signs here. So I can always move the phases around, and I choose the phase such that there is no phase here, but there is a phase here. Now, we also have parity symmetry, parity of H of sigma.
Sorry?
Just 1 second. P inverse is H of minus sigma. That's clear from this. We just reverse the orientation, so sigma flips sign. Yes?
The minus in the T above is up to a power, is raised with a power of L, or is minus for L odd or even? This
Sorry?
T sigma plus 2 pi equal to minus T sigma
That's for every L.
for every L.
For every L. Because what it cares is only what happens at one site. That's the beauty of this. If you look at the symmetry group, you say, okay, for L odd, we know that it is in a projective representation. So, okay, I don't care about L odd, I only care about L even. So for L even, if you introduce the twist, you see that something is projective. That will be very important soon. So this is parity. For generic sigma, it's not a symmetry. But for sigma equals 0 pi, it is a symmetry. But these relations of, where was my R?
There below.
Ah, here. So what this guy does is very similar to that. So this Hamiltonian has a P prime symmetry, which is R times P, and that commutes with the Hamiltonian. Because parity flips the sign of sigma, and this guy, it acts sort of like charge conjugation, also flips the sign of sigma, and together it's a symmetry of the problem. However, P prime T of sigma is T of sigma inverse P prime, and P prime e to the I xc of sz is e to the minus I xc sz times P prime, and P prime square is minus 1 to the L. Okay, so we have some relations in the group. So we have a symmetry transformation that acts. That's U1 that exists for generic sigma. We also had this R that exists in special sigmas. We have parity-like transformation, or CP, that exists every sigma, and its square is minus 1 to the L. Again, we could redefine P prime by a phase, such that we have here 1, so that P prime square is 1. But then this phase will haunt us elsewhere, so I picked that choice. And finally, for sigma equals pi, so for sigma equals 0, we have the full SO3. For generic sigma, we have only U1, and R is not a symmetry. Sigma equals pi, we also have this Z2 of R. It is a symmetry, and you can check that T of pi, the sigma equals pi, times R, is minus R T of pi. So that at sigma equals pi, we also have something projective. At sigma equals pi, what it does is to put minus signs here, That's the only change in the Hamiltonian. It is a very special defect when we have a minus sign. And we still have the translation symmetry, and we still have the O2 symmetry, but the O2 and T fail to commute. The commutator is -1. I emphasize that so far I use very little of what the Hamiltonian is. So you asked me about the sign. Are you too cold? You can close the window.
The lecturer
Sorry?
The lecturer objects from the clothing below.
Well, I opened it intentionally at the beginning, and now that I think we got most of the viruses out. So if somebody wants to close the window, that would be fine. I'm also heating up as I talk, so it doesn't matter.
You didn't write an explicit expression for the generator of the symmetry for different values of sigma, right?
I did. It's the same thing. It doesn't change. It's the same thing.
Well, what do you mean? If, for instance, this O2 symmetry, then it won't be just...
The U1 is e to the I xi, and R is what I wrote. R is this. Where did I write R? Here. Doesn't change as a function. It doesn't change as a function of sigma. Okay, so the Hilbert is the main hero here. We assumed some symmetry. We assumed SO3, but if we added the blue lines the blue terms, these guys, it would have been essentially the same, except that if the two are the same, I can still turn on sigma, same way, and if they are different, only sigma equals 0 and pi are meaningful. So the symmetry is Z2 times Z2. Okay, I really emphasize that what I'm using is very, very little about the structure of the Hamiltonian. I use the global symmetry and the structure of the Hamiltonian. So what do we do now? Now that we have...
Nothing?
Yeah.
Do you have any discrete components to the symmetry which commutes with the...
in addition to SO3? No.
No, I mean subgroups of SO3. In addition to SO2 and U1.
There are many subgroups I could use. I started with generic sigma. So for generic sigma, I can always conjugate it to be along the z direction, and sigma is the same as minus sigma. And then there are very special sigmas, which are 0 and pi, where I forget what it's called. The centralizer is bigger.
Stabilizer.
Sorry?
Stabilizer.
The stabilizer, right. Well, actually, it's the same thing. And people use the same terms. Anyway, it's the set of transformations that commute with G. Okay, so after the long preparation in all the previous examples before, now we can go to work. And what we should do is compute the partition functions of the trace of the Hilbert space of this thing. Yeah.
Is there a Hamiltonian ansatz that satisfies all these topological properties?
Okay, so first of all, there's no topological property, number one. The Hamiltonian that was written by Heisenberg describes these spins and how they interact with nearest neighbors, imposing either SO3 or O2 or Z2 times Z2, depending on the coefficients. There are other terms we can add that respect the same symmetries. I can add them just as well, and they will not affect what I'm doing.
I meant age of sigma.
H of sigma, well, once you give me H, and once you give me the twist that you want to do, there are various ways of implementing the twist. For example, I can move it around. I can, as I showed, you can also spread the defect homogeneously in space. You can also spread it inhomogeneously. What matters is the total holonomy should be that group element. And we have done it in a number of examples before, and now I'm following the same recipe here.
So, David, before you go to the partition function, how is the spectrum, the ground
I discussed the spectrum. I promised him that he would regret asking about translation, and I promise you you'll regret asking about the spectrum. The spectrum is a more detailed question that depends on what the Hamiltonian is. And we might also be interested in the spectrum for this particular Hamiltonian or another one when L goes to infinity. We will do that. But I would like to keep L small, 52, 4, and say what we can say about this system. Later we will specialize to a particular Hamiltonian and a particular limit. But for the moment, I just want to keep the discussion general, because that's what we give, this is what gives this method the power. Yeah.
So can you just maybe illustrate how so
Well, you commute. Commute commutation relations. These are Pauli matrices, and you just commute them.
Yeah, yeah. Okay.
And yeah. Okay, so what do we compute? We compute a partition function. It's very similar to what we did in previous times. There is a beta, which is e to the minus beta h. There is L. Sorry?
When you are writing S1Z, that means the first site S1 is G. When you are writing it for I sigma,
The subscript is the number of sites,
yeah, okay.
and when there is no subscript, it's the
Then
sum
it's
of them.
summed over there.
Yeah, I think I had it somewhere here.
Yeah, you wrote it, but
Okay, no, it's good to remind people. Please stop me, because otherwise I'll tell you more things and you will not understand. So please stop me. So L is the number of sites, and there is a sigma which tells us which twist we did in space. And I also introduced two more parameters, C and N, and this is defined to be trace e to the minus beta h of sigma, same Hilbert space, and then we put here S Z and T of sigma to the nth power. So what was the rule? Compute trace e to the minus beta h. H is the twisted Hamiltonian, and what we put here is an arbitrary element in the symmetry group of the twisted Hilbert space. So this is an element of the twisted Hilbert space. For special values of sigma, we can do more interesting things, and maybe we do them. But for generic sigma, we can put an arbitrary U1 transformation and an arbitrary translation. Right? This is the translation corrected by the twist, as we did. And if we're very powerful, and we have a specific Hamiltonian, we can calculate it. For small values of L, you can do it by hand. There's a small number of states. For L of order 20, 30, you can even do it with Mathematica. You just compute the trace. It's a function of all of these things. But without doing any computation, we can derive certain consequences. Beta, L, sigma plus 2 pi. So it's very repetitive, and it's good that it is repetitive, because you see that this is an algorithm that works in all possible systems. So I'm not going, we did it last time for the compact bosons, and now we do it for this system. And this thing is minus 1 to the n, z beta L sigma c n. Where did this come from? When sigma goes to sigma plus 2 pi, nothing here changes except this guy. And that guy picks a minus sign from here, so we get minus 1 to the n. So naively, sigma and sigma plus 2 pi should be the same, right? This is a background gauge field that in the space direction. It should be the same, but it's not the same when n is non-trivial. We can also have another relation, beta, L, sigma, c, n plus L. These are periodic boundary conditions. We just go with, we put here t to the n plus L. And then we use this equation, so it gives us e to the I sigma sz. We did something very similar last time, so this is beta, L, sigma, c plus sigma, n. That clear? I just use this equation inside the trace. Another way of saying it, I'm using the group relations to relate the partition functions at different values of the parameters. You can also have z of beta, L, sigma, c plus 2 pi, n. That is minus 1 to the L, z, beta, L, sigma, c, n. Another thing I can do, I can take this guy R. It's not a symmetry. This R, it's not a symmetry. But I can put R inverse here, cycle it through. It doesn't commute with H, it doesn't commute with this, but it gives us a relation that Z, beta, L, minus sigma, minus C, N is Z of beta, L, sigma, C, and N. And we can also do the same thing with P prime, which is a symmetry. So it's getting a bit tedious. Z of beta, L, sigma, C in N is the same as Z beta L sigma minus C minus N. And you can check it for yourself. Now, there are some phases here. There's a phase here. Let's circle them because they are, the phases are the hero of the story. There's a phase here, and there's a phase here. And throughout the discussion, I said that I had some freedom. I could have moved things around, could have redefined T so that I don't have a minus sign here, but then I get it there, etc., etc. All these redefinitions, I don't even need to discuss the operators now, because all these redefinitions amount to multiplying Z by a certain phase that depends on the parameters. So your Z might be the same as mine times e to the I sigma times xc over 2 pi over 4 pi, whatever. You can do any such redefinitions. And as you do that, the phases will move around, will change. But it is a fact that you cannot get rid of all of them. Was a question? And at sigma equals 0 and pi, we have a larger symmetry. And therefore, we can study more partition functions. Also, we can study the partition function with an insertion of p prime. With p prime is a discrete, either we insert it or not. So we could study with the insertion of p prime, that's always a symmetry. And we get more relations. Where is the blue? This relation and this relation affect only the internal symmetry parameters. Because either we go 2 pi around space or we go 2 pi around Euclidean time. They do not involve spatial symmetry. The translation symmetry and so forth. This relation, on the other hand, oh, and this is also true here. This double arrow relation and this double arrow relation involve also space-time transformations as they affect N. And we see that we have phases. What do the phases mean? So mathematically, they mean that the partition function is not a function. I'm repeating myself, and it's worth repeating it first because it's correct, and second, because you see that it's the same set of words again and again and again. What they mean is the partition function is not a function. The parameter space involves sigma, which is a circle, but as we go around the circle, Z does not come back to itself up to a sign. The same thing is true with Xi. And we could have redefined things, but then we would have phases elsewhere. In order to show that you cannot get rid of all the phases, you really need all the relations. You left out one of the relations, you can redefine things, but you really need to keep the other relations. Yeah.
Maybe it's, I don't know, naive, but it's kind of expected that you come back, if you take a system of spins, it comes back to itself after a 4 pi rotation and not 2 pi rotation.
I emphasize that the relevant thing is the global symmetry.
So it's because we have SO3 that you...
The global symmetry was SO3, so I come back to where I started in SO3. Notice that the Hamiltonian as a function of sigma came back to itself. Hamiltonian was even invariant under the 2 pi, of going back to 2 pi. It's the Hilbert space which is not. And even when the Hilbert space is invariant, when L is even, so when L is even, we don't have the minus sign here, we still have the minus sign here. So the translation operator is odd under these 2 pi, shift of sigma. And so the translation operator is odd under that. So how should we think of this? It's an anomaly, and then we can ask an anomaly in what? That's the key thing. Any suggestions? What's it an anomaly in? What is it it's an anomaly in? What's the symmetry group that this is an anomaly in? First of all, we have an SO3. But there is no anomaly in SO3. On general grounds, there cannot be an anomaly in SO3. What we have here is an anomaly mixing SO3 and ZL. It's an anomaly between lattice translation and SO3. I could not introduce a twist in the ZL in space. Superficially, we can say that changing L by 1 is a twist in ZL. That's not precise. But we can study the Hilbert space as a representation of ZL. And the Hilbert space is a projective representation of this ZL times SO3, or the subgroup of it that is preserved by the defect. Yeah?
Sorry, I'm trying to understand like what are you saying. Is the point that this is not a direct, like that the symmetry group is not a direct product?
Actually, for sigma equals 0, the symmetry group of the system with sigma equals 0 is a direct product. For other values of sigma, the SO3 is gone, and it becomes U1, and the U1 mixes with the ZL.
It's not even a ZL, right? It's a Z-sim. Like you don't even have a, it's not L-period.
That's correct. So the group of the symmetry group is a group of this twisted Hilbert space. In this particular case, you can actually, at the level of the group, you can multiply that by the 1 over L root of that. So let me call it T tilde of sigma, which is T of sigma, e to the I sigma over L as Z. And then it satisfies the L relations. This is a peculiarity of this particular system. In general, if I have a discrete symmetry, I couldn't do that. So if the symmetry had been Z2, the thing on the right-hand side would be a Z2 element. And if L is even, I cannot redefine by it.
No, but the action here is...
Let me say it in a more mathematical way. What I put here is that I localized the flat connection on one link where I have a transition function. I could have instead spread it homogeneously. For some groups, I can spread it homogeneously. So there's every link I had. So I said the holonomy was labeled by G. If there exists a G prime, such that G prime to the Lth power is G, then I can redefine T by a factor of G prime, and then the symmetry group as a group would be still, the translation would still be ZL. This is the case if I spread the holonomy homogeneously. So the connection is constant, and there is no transition function. Then we have a manifestly ZL, and the rest in the U1. So as a group, it is as it was.
But it's not a direct product.
It is a direct product in that case. In that case, it's a direct product. But this direct product hides the physics. The physics is that the defect is localized. And if I am away from the defect, I don't want to see any connection or anything. So I would like to trivialize the bundle in such a way that in most of space, nothing happened. I only change physics in one localized region. So I put the connection to be 0 everywhere, and there's some transition function somewhere behind Andromeda. And I'm doing experiments here, and whether there's a transition function around Andromeda or not, it makes no difference here. And I would like to use the same operators that I would use if there had not been a defect there. So there's a mathematical term for that. We have a group and a choice of generator. I think that's the words. But I'm not a mathematician, so. In any event, whatever name you give to the group, I wrote the relations here. And what we see here is very peculiar. We have what we can call an anomaly, a mixed anomaly, between the internal symmetry and the lattice symmetry. And it's well defined in the sense that this is the symmetry group. I first do the twist in the internal symmetry. In the time direction, I can still put a twist in the internal symmetry. In the time direction, I can still put a twist in the internal symmetry. But now things start mixing with the translation symmetry, and we get these funny phases. And as I was asked before, it still doesn't matter what the Hamiltonian is. Hamiltonian played no role, only the symmetries of the Hamiltonian. Next, we do what we did before. Let's take beta to be very large. If beta is very large, we focus on the low-lying states. So these formulas are true for any beta. The phases are independent of beta. And therefore, we can try and compute that in the low energy theory. L is finite. So I'm just looking at the low energy theory. So for simplicity, let L be large but finite, 100. So we look at the low energy theory, and the spectrum of the Hamiltonian should be such that we still get these phases. So imagine the solution of the system is a unique ground state for every sigma. So every sigma is a unique ground state. As we solve the system, we're very powerful. We diagonalize the Hamiltonian. There's only one ground state for every sigma. If that had been the case, we couldn't have these phases. How can we have phases? We can have phases if there's more than one ground state. For example, some symmetry was spontaneously broken and there are a number of low-lying states. Or, if, as we vary sigma, there's some level crossing. And if we think of L as being large but finite, in order to have level crossing, as I change the parameters in the Hamiltonian only on one site, right? So we have a billion sites, and I'm changing sigma only here. Don't touch anywhere else. In order to get any level crossing, it's clear, David already gave the answer. If for the two states to cross, the energy difference between them should be small. So specifically, the energy difference between them should be of order 1 over n. So what do we learn? Again, I don't even care what the Hamiltonian is. I didn't solve the system.
You clearly says that it has to be symmetry generator, so that's all you
I needed a symmetry. All I used was a symmetry. I used translation symmetry, which was ZL with periodic boundary conditions, and I used the fact that there's SO3 symmetry. And in fact, I said that it's enough to have Z2 times Z2. You can run the whole story just with Z2 times Z2. The Z2 of sigma equals 0 or pi, and what I called R, they are enough to run the show. So what we learn is that at low energies, either the spectrum is gapless at large L, so the whole spectrum collapses down and we have lots of states at 1 over L, or some symmetry is spontaneously broken. Well, it can be spontaneously broken. The SO3 cannot be spontaneously broken. Who can tell me why?
Within one dimension.
I'm in one dimension. So the SO3 cannot be spontaneously broken. So all we have at our option is ZL. Translation symmetry is spontaneously broken. This is the statement of LSM, which was sometimes in the 60s, that in this system, based on general considerations, which in hindsight can be mapped to what I said here, the system either is gapless at low energies, or there's spontaneous symmetry breaking. And now we can change the Hamiltonian, and we can flip the sign as you wanted and check what happens. So if we flip the sign, it's a ferromagnetic, and then symmetry could, so it could either be ferromagnetic or anti-ferromagnetic, and we can change the parameters, especially if we add the blue terms, And as we add the blue terms, we can actually explore options where the spectrum is gapless or the translation symmetry is spontaneously broken. And if I have time, I would do that. Zohar, you had a question? Or you're just stretching?
Well, I think there is some jump in the logic. I think what you actually proved is that at some sigma there is a phase transition.
I'm at finite L.
Sorry, that at some sigma there is a twofold, maybe...
Twofold degeneracy, that's the
Twofold
first thing.
degeneracy.
Okay, so I'm at finite N, it's a finite dimensional
Right,
Hilbert space.
so-
What I showed is that there is level crossing at some sigma. So let's plot these two states that cross. So at sigma equals pi, they cross.
Yeah, but from here to say that you know something about the spectrum at 0 sigma, which is what LSM was
Yeah.
about historically,
Yeah, no,
there is a jump.
actually, what LSM, this part of the argument is exactly the same with LSM. It's exactly the same as LSM.
But
They,
there is a jump.
they presented two variational wave functions. One of them is this and the other is that.
Yeah.
But when I don't think there's a flaw in my logic, because L is big and finite. L is big and finite. So if L is big, the defect is very far. So I changed the Hamiltonian around Andromeda. Changed one site. I flipped by 1 over L. Just one site. How can it be that I have level crossing that I can detect here? The only way this could happen is if this is of order 1 over L. That's the only way it could happen. This is where locality enters. So what I have here is, unlike the case that you and I studied, where there was level crossing as a function of theta, so this sigma appears very much like the theta that we had. But here, it is not a parameter, merely a parameter in the Hamiltonian. It's a parameter associated with the global symmetry of the system, and it is a localized defect, which is very far. So if this is the new element. I don't just have a Hilbert space that depends on sigma. I also have this locality that the defect can be put arbitrarily far away. So that tells me that there must be a 1 over L here. And that's exactly the statement of NSM.
Yeah, but I think there is always has been a jump. Like
What jump?
nobody proved that it's not 1 over log, and you need more input.
No, you work a little bit more, you will see that it's 1 over L, just by scaling it.
Yeah, you need more input from locality and kind of.
I'm happy to discuss it in more detail, but it's clear that something will have to, at finite L, and there is no discontinuity, because we are at finite L. So, that's very, I'm not taking any limit. In fact, I use very little about the structure. The input is very minimal, much less than the input in all the later developments. And in fact, as I said, here sigma is continuous. So there's a version of the story due to Oshikawa where he uses adiabatic parameter like this sigma, in which he changes adiabatically and he tracks the states, very similar to that. But I can do that for sigma equals 0 pi. I have only 2 sigmas. That's good enough. I don't need any adiabaticity. That's good enough in order to run the argument.
Yeah, you can prove that it actually happens in sigma equals pi here.
In this case, it's easy to show because it comes from the enhanced symmetry at sigma equals pi, there's an O2, and this O2 is actually realized projectively. Yeah, so
You're using P prime.
so you use P and P prime. You really need to use all of them. If you didn't use R, if you did not use some of these relations, you could have redefined the phase away, and then it would not be an argument. So if we had only U1 in translation, I couldn't have used this argument.
I guess another interesting application of this idea is that it's been known that for spin 1 there is no gapless point.
For spin 1, all these phases are absent.
Yes.
Yeah. Yeah, you can change that in a billion different ways, but what I would like to do in the remaining time,
L is not known.
sorry?
What if L is not
I'm going to do L equals 2, but for that, which actually is quite interesting. I solve, well, depending how much time it takes, I'm happy to solve L equals 2, 3, and 4 on the blackboard for you. And you will see that, let me just put a teaser if I don't get to that. So from that, it looks like the periodicity in L should be mod 2, because if L is even, it's in an SO3 representation. If L is odd, it's in a projective representation. And indeed, we have only -1 to the L here. And these phases reflect a mixed anomaly between this and that. So I'll say something which would look totally outrageous. For this particular Hamiltonian, at large L, you can prove, in fact, you can see it already for small L, that the periodicity is mod 4, not mod 2, which actually was known from Bette's exact solution and was checked numerically by various people. And I think we were the first to give the conceptual explanation why it's mod 4 and not mod 2. And this conceptual explanation involves a self-anomaly of this ZL, not a mixed anomaly between this and that. This is a much more subtle anomaly, and that more subtle anomaly involves only the ZL. But that's more advanced. For that, I need to give more information.
What is already on the board? Do you need the full SO3 or just the U1 sample?
For what's on the board, I need Z2 times Z2. So there's a sequence of symmetry. I presented it as SO3. This is how it was originally presented. Then you can embed an O2 in it. The O2 is generated by U1 and the Z2 that I called R. And in fact, it's enough to do Z2 times Z2, subgroup of that. That's enough. So if you turn on generic alpha x and generic alpha y, you have only this symmetry, and this reasoning still applies. Just substitute sigma equals 0 pi here, and c equals 0 pi. And in the reference I gave, it was worked out in all gory details. This is 0, this is pi, pi is 0, etc. You have these phases.
The level, this is the level as a function of sigma, and they don't cross exactly at pi.
Because cross exactly at pi. Because at the point
like,
pi,
it's like in the theta bar.
sorry?
Similar argument to the theta bar.
Yeah, it's very similar, and even the group theory is very
So
similar.
it should close cross at exactly sigma equals pi.
Yeah, because there's a symmetry that guarantees it. But a priori, it could be more complicated. You know, it could be, yeah, it could be more states and whatever. Yeah, it could be much more complicated with lots of crosses. What happens at sigma equals pi is, as I said, there's an O2 symmetry, and that O2 is actually realized projectively, and that is associated with the degeneracy here. Okay, I'm running out of time. What does this have to do with the continuum theory? So now the Hamiltonian is more important. So we take the same Hamiltonian, and for simplicity, let me ignore these blue lines, and these blue terms. And this system flows at long distances to the SU2 level 1 WZW1. And that's a special point on the C equals 1 line of conformal field theories that we discussed earlier in these lectures. And how are the symmetries embedded? So the global symmetry here is SU2 left and SU2 right mod Z2. And for generic radius of the C equals 1, we have this symmetry that we discussed. So at this particular value of the parameter R, this symmetry is enhanced to that. So that symmetry is a diagonal SO3. And that diagonal SO3 is the SO3 that we saw with the naked eye. If that had been all there is to it, we would not have gotten the answer.
This is not just two Dirac fermions?
No. It's at a different radius than two Dirac fermions. So first of all, it's one Dirac fermion, not two. And second, it's at a different... I know what I'm saying. If at all, it's one Dirac fermion because it has C equals 1. Two Dirac fermions have C equals 2. But in addition, it's a different value of the radius. It's not the same as any number of Dirac fermions.
So what's the mean of it at k equal to 1 with U2 7?
No, I didn't say U2, I said SU2. Well, you don't like it?
No, I mean, okay, so,
I stand behind what I said here.
so
And I see Zohar nodding his head. I think he confirms that this is the answer. Sorry? Yeah, that's the answer. And this answer is known since the early 80s, long before people knew about SU2 level 1, or more or less the same time, mid-80s. Yeah, that's the correct answer. And there's an SO3, but that could have been puzzling. It could have been puzzling because there's no anomaly in SO3. Where are all these anomalies? Question number 1. We have only SO3, there's no anomaly within SO3. Where are all the anomalies we discussed before? Let me ask another question. The spectrum of the Hamiltonian is known. The spectrum of the WZW model is known. It starts with H bar. So it starts with a state with SU2, J left, J right. So So it starts with a 0, 0.
I apologize, but when you say there's no anomaly in SO3, you mean quantum mechanics, because previously you had the finite remaining degrees of freedom. In 1 plus 1, there is a possible SO3 anomaly.
That's correct, but we sort of have that for odd L, but I would like to take the limit with even L. I can say much more about that. In fact, what I'm saying here is only true for L even. Otherwise, the spectrum of the Hamiltonian is different. But let's stick to L even. I'll do L odd if you want. I'm not going to raise the puzzle already here. So L is even. We have SO3. On the lattice, it's realized linearly, not projectively. It is this SO3, and there's no anomaly in this SO3. That's the first level. Then, at a quarter, we have states in a half. And under the SO3 spin, this is 0, and this is 1 plus 0. I just multiply the representation. Let's look at this guy. This guy is invariant under SO3. Right? This guy is invariant under SO3. Has dimensions a quarter. So the total quarter, let me write the sum. The sum is a half. It is very, very relevant operator. There is no symmetry in the low energy theory that forbids it. Yet we claim that this is the right answer. We claim that this theory is gapless, and it has an emergent SO4 symmetry. Right? Where was the SO4? This is SO4. There is an emergent SO4 symmetry. And nothing in the SO3 forbids this term in being present in the Hamiltonian. Why isn't it there? Well, we've seen an example of that earlier in these lectures. There was a symmetry at long distances that was not present at short distances. And we called it an eminent symmetry. The low energy theory, so this is a fact. You could ask this. Whenever people started understanding the renormalization group, emergent symmetry is relevant, irrelevant, this question should have been asked. And it was asked. Why is this operator not deforming the Hamiltonian given that it is invariant under the SO3 global symmetry of the system? We have a relevant operator, preserves the SO3, violates the SO4. Why isn't it there? And the answer is, as we'll soon discuss in detail, this operator is allowed by these symmetries, but there's another symmetry in the problem, lattice translation. It's non-invariant under lattice translation. So this one is non-invariant under lattice translation, and therefore it can't be there. How does this fit into the general picture? So for the older members in the audience, in the case of Kogut-Susskind fermions, they are also massless fermions, and they are not protected by any internal symmetry of the original lattice system. They are protected by lattice translation, not to be confused with continuum translation. So what we see here is that the IR theory has an eminent Z2 that started its life in ZL of lattice translation. And under this Z2, this is plus, and this is minus, and this is minus. So this operator is odd under the eminent Z2 symmetry. But it's very important, there is no Z2 in the microscopic theory. What happens at long distances is that the original ZL, typically it would go over to U1 of translation in the continuum. But here it goes over to ZL times Z2. This is continuum translation. And this is an internal symmetry. So we started at short distances with ZL. We'll also say in more detail how this thing happened. Group theoretically, we started with ZL. And at long distances, we end up with U1 times Z2. This Z2, this U1 is ordinary translation of the continuum. And this Z2 acts as an internal symmetry. And this internal symmetry forbids operators. It forbids this one in the action, or in the Hamiltonian. It also forbids all irrelevant operators that violate the Z2. So this Z2 is not merely an emergent symmetry. It is a symmetry that was not there microscopically, but it's much more powerful. Just once, let me finish the sentence. The Z2 was not there microscopically. There is no Z2 group. This one is not a symmetry. But at long distances, it acts as an exact symmetry. It's not even violated by irrelevant operators. What did you say?
I got the impression that this Z2 was there as part of ZL.
It's not a subgroup of ZL. It's not a subgroup of ZL. More precisely, it's a limit of a quotient of that ZL. But it's not a subgroup. There's no Z2 that acts on the lattice. Sorry, I'll expand on that. Speaking
conventionally, the intuition is that even L and odd L are kind of very different. So somehow this.
I mean, even L, I'm not even considering the odd L system.
But there isn't.
Sorry?
But there is an odd L system.
There is an odd L system. I'm happy to, I'll discuss
I
it.
think what's been said here, which is that since even L and odd L aren't the same in the microscopic theory,
They are not the same.
why not?
Because I can tell you what
Well,
the
if that's
spectrum
what
is.
you want it to say.
Okay.
There has to be something like this.
I wasn't planning to say that, but if L is odd, I can continue this table. In a different color, L odd. The lower-lying states are H, H bar, J left, J right, and they have quarter zero, which is a half zero, 0 a quarter, which is 0 a half, and then there are other states. And the J, the total J, which is the sum, is a half plus is a half here. And this is a half, and then there are other states. So the spectrum of the Hilbert space for L even and L odd is completely different. This is known as twisted Kac-Moody, this is Kac-Moody, this is twisted Kac-Moody. The spectrum of the Hamiltonian is completely different. And one thing we would like to interpret is what's the relation between this and that? That's an interesting question. And the answer is that in the continuum, not on the lattice, we have a new Z2 symmetry, this eminent Z2 symmetry. And if we have a new symmetry, we can put a defect in that Z2. So in the continuum, but not on the lattice, this system is obtained from the same conformal field theory by putting a defect of the Z2. It does not yet explain why I claim the L periodicity is 4 rather than 2. This explains why there is a Z2 periodicity, why L even and odd are different. I claim that there is a mod 4 periodicity, which is more subtle, and if we have time, we'll get to it. But L even and L odd, the spectrum in the continuum is different. And I claim that already for L even, there is a puzzle. If you don't see that there is an exact symmetry in the continuum limit, which is not a symmetry at the microscopic level, then it's puzzling why this operator is not present. You have to impose the extra symmetry. Another way of seeing that there must be a Z2, another Z2, is you could say, how would a low energy observer in the continuum tell the difference between L even and L odd? Because locally everything looks the same. How come they are different? There must be something in the low energy theory that allows me to change the limit from L even to L odd. And I say it's the same Z2, just as it excludes some operators, it is interpreted as a defect of that Z2, gives me the twisted theory.
Just to make sure, this difference between L odd and even is only true for the antiferromagnetic.
Yep, that's correct. This whole story is
Everyone
only
is the same.
this whole story is only for the antiferromagnetic phase. I said it sometime. Now we're going to limit ourselves to that. And was another question here? Was a hand? Okay. And this Z2 can be identified group theoretically as in the center of SO4. There's an obvious Z2 with the center of SO4, and that provides the twist.
Can't you say that this Z2 is manifest on the lattice? Because on the lattice there could be a topological twist defect where you add another lattice site.
That's not a defect. On the lattice, so, okay.
You enrich the Hilbert space, it's good.
Okay, I can give you a 2-hour lecture on that. And some of that is summarized in the paper. Intuitively, you could say that changing L is like a twist in that Z2, except that one, there is no Z2. There's no Z2 symmetry to begin with. There's no subgroup. Second, as you add a site or subtract a site, you do it twice, you don't come back to where you started. And the real kicker is that if you think this is a twist by Z2, you could say, what's the symmetry of the twisted Hilbert space? It should be the centralizer, or what was the other word? The stabilizer of that group. And here what happens is the ZL becomes ZL plus 1. It's not the stabilizer of anything. The symmetry is not a subgroup of the old one. It's not the stabilizer. And I can go on and on why there is a sense in which what you said is correct. That people even said that in the literature, that changing L, they say it's a background translation gauge field. These are the words. I don't understand a single word in this sequence.
It could be a topological defect, not a symmetry.
Okay, it could be a non-invertible symmetry defect. It could be all sorts of things. It does not follow the standard rules. What I did here was to take these standard rules, apply them just took the system and I did the conventional things. Now we can elaborate and do that in all sorts of ways. Okay, I'm going to take a shortcut to the answer to answer David's question. Because before we get into what happens microscopically and whether we could go beyond the regular rules, we would like to understand group theoretically better what happened here. How did this thing happen in the first place? And that's not what I prepared, but let's diagonalize the Hamiltonian. And I plan to do it in detail, but so that's the energy. And that's e to the 2 pi I times the momentum. Oh, that's right. P, where T is e to the I P. Right? K. I want to need another letter. Call it K. K is usually an integer. R, this is IR. Right, these are the eigenvalues of T. Right, so I just pop it here. Special values are 0, pi, and 2 pi. And momentum R is 2 pi periodic. It should be Lth root of unity because T to the L is 1. And let's assume that sigma is 0. So there's no sigma, T to the L is 1. So we can put here an integer over L. Let me do it this way actually. N over L, and there's a 2 pi. And this is N 2 pi N over L. Okay, so we diagonalize the Hamiltonian. What do we find? We find lots of states here and lots of states here. That's the spectrum of the Hamiltonian. There are states near t equals 1, and there are states near t equals minus 1. And let's for simplicity be L even. You can repeat that for L odd. So that's the spectrum. We're very powerful. We put it on the computer, I don't know. And we diagonalize the Hamiltonian. There is no Z2. We could take any state here. If it's around here, we could say, we could say that there's a Z2, and these guys are odd under the Z2, and these guys are even. And for low-lying state, it makes sense. Say, okay, this guy is odd under the Z2, and the momentum of it is the deviation from pi. And these guys are even under the Z2, and the continuum momentum is the deviation from 0. We could have said that. However, if we go up here in this spectrum, there are more states. So what are you going to do about the guy here? Is it odd with large momentum, or is it even with large momentum? And even more so, a state here, should we say that it is even with momentum 0, or should we say that it's odd with momentum pi? There's an ambiguity. And indeed, there is no way to assign these charges. That's why there is no Z2 in the continuum. However, the lattice translation symmetry is, I'll call it C, some Z2 element, e to the 2 pi I, P over L, where P is an integer momentum in the continuum limit, and C is C square is 1, C square is a 1, and for low-lying states, there's a natural assignment of C is plus or minus, plus here if minus if it's here, and P is an integer, I take to be small, but if I go up in energy, to energy is above, around here, there is no way to separate them, only the product is meaningful. But as I make L bigger and bigger, the picture changes. To make L bigger and bigger, this thing becomes steeper, and this becomes steeper, and the energy here is of order 1, tilde across, and the energy, the momentum difference is of order 1 over L. So it becomes steeper and taller. So as I make L bigger and bigger, the separate assignments of charges for this factor and that factor is now meaningful. But it's meaningful only for high energy, for low energy states. For high energy states, it's not meaningful. So now we can see what
the critical error where they don't cross anymore?
No, no, they continue forever. They continue forever. And so for L equals 2000, you can go pretty high up in energy, and then they cross. Now, where would be an operator? Now, notice that what I'm saying now will be almost identical to what I said in the previous discussion of eminent symmetry when we talked about Philly constraints. Imagine we deform the operator. We would like to break the C symmetry. We are low energy people. We say, how can we possibly break the Z2 C symmetry? We need an operator that violates C and preserves lattice momentum, not continuum momentum. This is the guy sitting here. I'm going to interpret it as having vanishing lattice momentum, but odd under C because it came from here, from this triangle, and having large continuum momentum. So the only way to violate C in the low energy theory is to have an operator which violates C, and it has very large continuum momentum of order n. Alternatively, we could say that an operator that violates C and has vanishing continuum momentum sits here, but then it violates lattice translation. And we had an identical discussion when we talked about the filling constraints. So what happens here is that there are relevant operators that are charged under the windings, under this Z2 eminent symmetry. They exist. They exist as good operators, but they are not present in the action or in the Hamiltonian, because in order to be in the Hamiltonian, they have to be dressed with very high continuum momentum, so that the lattice momentum is 0. And that means that they oscillate very rapidly. So it's an operator of the form e to the I x n with very large coefficient. So their correlation functions vanish. They vanish in the limit because they oscillate very rapidly. So we discussed that at length when we discussed the filling constraints. And now we see another example of the same thing. And since I'm running out of time, I still owe you one thing. I still owe you two things. One, where is the anomaly? How does the low energy observer see the anomaly? So the low energy observer says, I have SO3 that started its life on the lattice. and I see an eminent Z2 symmetry, not an emergent Z2 symmetry. I see an eminent Z2 symmetry that wasn't there before, but I can explain why it is there because it started its life as part of the ZL. It emanates from the ZL. And there's a mixed anomaly between them. So the mixed anomaly between SO3 and the mixed anomaly between SO3 and ZL and symmetry, this mixed anomaly became SO3 times Z2 symmetry, which exists in the continuum theory. So we see here that we have a new symmetry which was not there microscopically. It is exact at low energies, not an emergent symmetry, not accidentally, it is exact. And it can have anomalies. And the anomalies in the eminent symmetry reflect anomalies in translation symmetry in the low energy theory. So for lack of time, I'm not going to explain to you why things depend on L mod 4 and why this dependence on L mod 4 reflects a self-anomaly of the Z2, which originates from self-anomaly in the ZL. From what I said here, it looks like there's a Z2 in the ZL. So what I really mean is that if you look at the spectrum, the operator C acts projectively on the twisted sectors. So for L odd and L even, let's say C on the ground state is I to the power L, not -1 to the power L. So if I look here, I say, okay, this guy is a plus sign. That was a natural assignment. And here, there are two guys. What assignment of Z2 should I give them? The natural assignment is actually plus and minus I. Not a half zeros. Well, pick one of them, 1, and you say, okay, this is I and this is minus I. And then you say, let's go to 4. When you go to 4, the natural assignment for 2 is actually to put a minus here. And the natural assignment for 4 is to produce a plus here. And if you compare 1 or 3 or 5, the plus I and minus I flip side. Let me say just one more thing, because I'm going to demonstrate it in a very, very vivid way. And all the skepticism about this Z2 and the sign will go away. And it will take me exactly 2 minutes, if I may. Let me solve the system.
How much time do you think you have?
I think I'm done, no? I'm looking at this.
So what are you planning?
2 minutes. And since I'm on the lattice, I'm going to take L equals 2. What's the ground? There are 2 states, and let's diagonalize the Hamiltonian. The ground state is plus minus, minus, minus plus. And we might want to put the 1 over root 2. Is that clear? The key point to watch is this minus sign. That's the key point. And that's something that you're not going to dispute. Then there are various states like plus, plus, and so forth. So the eigenvalue of t here is -1, and the eigenvalue of t here is +1. Because t moves the lattice, and because of the periodic boundary conditions, here it acts as -1, instead of 1. If you go to L equals 4, I can write the answer. You just couple the 4 spins, you diagonalize the Hamiltonian, and it turns out that on the ground state, we have +1, and on the first excited state, we get -1. So this one is the ground state that I talked about before. And this is a triplet at the next level. And here you see more states. The ground state here is even under lattice translation, and the ground state here is odd under lattice translation. So first of all, you see that there is a difference between 2 and 4. You see that here for L equals 2 and 4. But the same thing persists if you're looking at 2010. In 2010 plus 2, you can see that thing. And it also follows from this formula. So if you look more carefully at this formula, this I to the L pops out. Yeah, I met the 2-minute time limit. And if you're not convinced by that, I don't know what to do.
Can we talk about punishment?
For going over time?
That's one reason. But let's say we would have gauged on the lattice the various types of anomalies. We would make an attempt to gauge them. How would we be punished?
Okay, so you will not be able to do that because the symmetry that you can gauge is at best the SO3. Even that is not completely obvious because of the -1 to the L. And ZL, I don't know how to gauge. So this is how I got out of it. There's a fancier way to say that the symmetries that you can gauge are symmetries that you can make act on site. We can get into a long discussion what this phrase means. And just as I can give so the condensed matter physicists love this phrase, and different authors use it in different ways, and I can give you a long lecture about that. After I finish giving the lecture to Zohar, why you can and why you cannot think of changing L is a defect.
The condensed matter physicists like what?
Like, they like to think of, okay, the words they use, then you can ask what the words mean. So they will tell you that you can gauge a symmetry if and only if it acts on site. What does on site mean? Different people use different definitions. The strict definition is that the Hilbert space is a tensor product of local Hilbert space, and the symmetry group acts linearly on every site. This SO3 example, according to this definition, this SO3 symmetry does not act on site. Then there is another definition where we don't care how it acts on the local Hilbert space, we just care that it acts on the local Hilbert space, perhaps projectively. The second is actually the more commonly used definition. Some of the statements are not consistent with that, so we should use the stricter definition. Then the question is it an if and only if statement? Namely, can I gauge a symmetry which does not act on site with one definition or the other? Some people say that it's an if and only if statement. This statement that I just said is manifestly false. Is manifestly false. And we saw that in the example in the last lectures where we had symmetries that had an anomaly, had both momentum and winding. And you could ask, do they act on site or not? And there the answer depends on whether we work in the big Hilbert space before we impose Gauss law or after we impose Gauss law. So the lesson from all that is that when you use this language, and furthermore, if you do T-duality, what acted on site with whatever definition becomes not on site and vice versa. So every one of these statements needs an asterisk with all sorts of legalese, except when this thing with that thing and so forth. So I do not know a general recipe how to deal with that. But on a case-by-case basis, I know how to couple to classical background field, not dynamical, classical background field, symmetries that act on site in the stricter sense. That's straightforward. This is the same as Leibniz gauge theory. But also symmetries that do not act on site. Some of them I know, like this is what we did last time. We had twists both for momentum and for winding. The defects were obviously there. And then there were subtleties as we tried to move the defects around and so forth. But I do not know a general recipe how to do that. On a case-by-case basis, we can do that. And it seems to me that if it's on-site, it's easy. If it's not on-site, then we don't know. And then it might even be that the symmetry does not act on-site, and yet there's no anomaly, and yet you can gauge it. Because one way out would be that there's a dual presentation of the same theory where it is on site, and then you just do it in the dual variable, and then you can translate back. So I don't want to give any blanket statement.
Okay, let's thank Navi for the whole.